computer. Okay, welcome to our first seminar. I am very pleased and also very grateful to introduce Ayşe Eren to all the listeners. And actually, she has a bio which I would like to talk about very briefly. Give me a minute. I'm not very much prepared here. Right. Okay, she was born and raised in Istanbul. She was one of our previous students, one of our very good students. She had her bachelor's degree and master's degrees from our department. And during her Master of Science, she was studying computational enzyme dynamics. And in 2017, she went to Indiana, United States, to Purdue University Chemical Engineering Department, and she started studying their process intensification for pharmaceutical crystallization, and she's about to finish her PhD, hopefully soon. And now the floor or the Zoom screen is yours, Ayşe. Thanks again.
Okay, yeah, thank you for the introduction. I tried to help you with the intro with this small introduction slide, so I hope everyone followed it. So I'm just going to jump into it. This is the outline of my talk today. I will explain why I work on crystallization. I will try to motivate my work and what crystallization is. And then I will show you some workflows that we developed for my research, and then a little math without boring you so much. And then I'm going to show you 3 examples from 3 different projects that I worked on. And then I will wrap up, hopefully. And during my talk, I will try to relate my work to the lectures that I took during my graduate studies in Bogazici University and Purdue. And let's start. So crystallization is basically a separation process, and it has a lot of applications. So this is how I like to put it. It's the transfer of mass from one medium, from gas or liquid, into organized solid structures. And these are special structures. They help people a lot to realize new research, very cool research, from energy to pharmaceuticals, food, or biotech. And here there are some examples that I put here if you want to read through. But today I will mostly focus on pharmaceutical crystallization. Here as shown, basically the powders that we use, like salt or sugar, they look like salt and sugar, but inherently they are crystals. And these are the materials that we take as drugs in our bodies. So yeah, that's why crystallization is important. And I will also mention a new paradigm. Lately, people in industry started shifting towards Industry 4.0. Industry 4.0 is smart manufacturing, as they put it. So basically, it is data-driven, more automated process to have more control on your process, to obtain what you need or what you want. It's basically using the data that we have been collecting throughout the days, months, or years, depending on your production, and then using that data to build a model of your process. And once you have a good model, which mimics your process very well, you call it digital twin. And now the paradigm says that use that model, use that digital twin, instead of going to the lab and doing more experiments, instead of wasting more time and materials and money, basically. So especially in the US, in pharma industry, people are trying to shift to this new paradigm, Industry 4.0. And an example I try to give here is like, we have these microscopes in the labs, and then we use them to look at our materials, or to understand what's going on. Now it's actually a lot of data. We have the new tools like image analysis or machine learning and everything, and now people are trying to find these strong correlations between the data they collect from microscopes and process parameters. So for example, here there's this material before it pre-treatment and after pre-treatment under electron microscopy, and you can see how the structure changes. And now we have the tools to correlate the, for example, black pixel areas ratio to white pixels to the pre-treatment process parameters. So whatever you can come up with, be creative and create these models to have digital twins so that you can do process optimization and have smart manufacturing. So that is the paradigm, and actually this is the basis of my research. And I will focus on, of course, the Industry 4.0 methodology in pharmaceutical crystallization. It is basic. I will show you basically some cool tools that we use to collect data, and how we call them process analytical technology tools, PAT tools, and how we make use of the data we collect and move from testing to design to control by data-driven, frameworks, basically. Okay. So, and very briefly, we are focusing on crystallization in pharma industry because it is in the heart of pharmaceutical industry. So after you find a drug compound, you do crystallization basically to form those particles and purify them. And then you process them further to have your tablets, basically to drugs, and humans consume these drugs. It is the first purification step. And then from experience and literature, we know that the properties of these crystals, such as crystal size or how the surface is, morphology, or which type of crystal you're producing, polymorphism, have tremendous effect on the further purification processes and also downstream unit operations. On top of the bioavailability of the drug, the stability of the drug, and how you manufacture it, and etc. So there are so many implications on, maybe not the implication, but the crystals, the properties of the crystals have tremendous effect on everything you can imagine in pharma industry. And this is a highly regulated industry. That's why engineers are interested in crystallization process to engineer these crystals. And as I mentioned, throughout the years, people have developed these tools to collect data, to control and monitor their systems. And now lately, we suggest that we can use that data that we collect from tools during the crystallization process and build a model, basically create a digital twin and do process optimization. So, everything can be smart and more under your control. You can produce the crystals that you want and, the drug that you want, basically. And this is the motivation of my work. This is why I work on pharmaceutical crystallization. Here, the workflow is, for my work is this. I try to put this simplified version here. It's basically chemical engineering. What I've been doing is literally chemical engineering. So I go to the lab, do some crystallization experiments to collect data and see what's happening in the system. And I look at the data to understand which mechanisms are active in the system, like crystal formation, crystal growth, or dissolution, etc. I will mention them in detail. And then based on what I'm observing, I create a model. I go to the literature, select a model which will describe my system the best, and then I find the unknowns of the model so that my model can mimic the actual system very well. And then I do more extra experiments to validate my model, to test my model if it can simulate the new experiments well, if it can predict the crystal properties well. And then once I validate it, it is called digital twin. I basically use that model to do process optimization or some design of experiments, simulating different experiments to understand my system further and predict what's going to happen without going to the lab more. Okay, so this is the laboratory setup that I've been using. So most of the work I'm going to show you will be about this setup. Excuse me. So this is a 500 milliliter jacketed glass container. Basically, you can call it a reactor to what we call it crystallizer, because we do the crystallization here. Here, as you see, there are a bunch of process analytical technology tools attached, PAT tools, on the crystallizer, and they're connected to a thermoregulator and a computer so that we can collect data and do some control experiments. So I use 3 of the PAT tools most of the time, which are shown in the brown box. One is UV. It helps me to measure the concentration of the drug compound in the liquid. The other is FBRM. It's a beam. Basically, it helps me to measure the crystal count or have a crude idea about the crystal size during the experiment, and also detect some crystallization events such as nucleation, growth, agglomeration, and so on. And I also use a camera, which we call PBM. Here you see the image from an experiment. And it is very powerful. You can do image analysis to support your crystal size data in real time. And you can also use this tool to actually observe what's happening in your system, like if the crystals are breaking or agglomerating or growing. So it is very useful, especially for model writing. And then I also use some offline characterization tools. After the experiment is done, I collect my samples. I use microscope or some other laser scattering techniques to characterize the crystal size, crystal shape, and also the surface structure, like morphology. So this will be the system I'm going to talk about. And I also worked with a mill to break down the crystals because, as I mentioned, crystal properties are very important. Sometimes you want to have smaller crystals or bulky but rounder crystals. So you may want to mill them down during the experiments and everything. So this is also another addition to my system that I use throughout my research years. And yeah, here also I'm mentioning the lectures that we took during our undergrad and during my master's years, and they were actually very useful. Like this is not staged. So okay, and the other, just to show you what I worked on, the other systems are continuous crystallization systems. So here you see 2 crystallizers connected via pumps and tubing. Here I worked on continuous crystallization of CBT for Mike Tyson. That's a very fun story we can talk about later. And here, as you see, this is the inlet. You continuously transfer your solution, make the crystallization happen, and then the crystal growth, and then you continuously filter your crystals with this simple setup. And this is another continuous system, oscillatory baffled crystallizer. Here you can see the baffles in the crystallizer. There's this oscillatory, I don't know, I forgot the name. Basically, you put the inlet and there's this like thing pushing your solution to up, and then you can create some cold and hot regions depending on your project to again engineer your crystal size or shape. And then from the top you withdraw your product again with a similar simple setup continuously. So yeah, these are also the other things that I work on. And again, while working especially with this crystallizer, I had to consider the heat transfer effects a lot. So I really had to go back to my heat transfer notes and like do some calculations to realize the research here. Okay, so very brief math. I talked about crystallization and I talked about model writing. Model writing is basically using differential equations. You did it a lot in your classes. So it's the same again, same old. Here we use population balance models, and I'm gonna introduce it hopefully without boring you so much. So crystallization happen. So I do crystallization experiments by using the temperature difference. There are other types of crystallization like anti-solvent addition or pH change, but I always do the temperature cooling crystallization. It's like making a jam. Basically, you put a lot of sugar in your solution while it is hot, and then you cool it down, and sugar basically crystallizes out. It's basically the same thing. And the driving force is supersaturation, which is determined by the solubility curve, with solubility of your material in your specific solvent, and basically how you cool it down. So you create this concentration difference, supersaturation. So, okay, in a crystallizer, first we have this clear solution, and then we cool down the system by using the jacket, and then we form the crystals, and then they continue growing, forming, or agglomerating. And what is happening here is actually the crystal size distribution, basically the number of crystals at different sizes are changing. I create smaller crystals, and while already created ones are growing and sometimes agglomerating. So your crystal size distribution changes, and we care about crystal size distribution because that's how we quantify basically the population of the crystal, like how this basically the population of the crystals. So this is something we care about because, again, as I told you, crystal size and shape affect almost everything later for your drug production. And what is really happening here is basically the number of the crystals at certain size is decreasing, while at other sizes it is increasing. So this is a number balance, what we are trying to simulate. And we use a partial differential equations to look at the number change during time and based on the length. And these are the equations define the events happening in the crystallizer, like nucleation, crystal formation, the disappearance of crystals due to agglomeration. So smaller crystals disappear and they start forming larger crystals, and appearance of the crystals, larger crystals due to agglomeration. And the change with respect to length happens with crystal growth, which is G. And all these equations are empirical. You can change these equations, and most of them depend on the supersaturation, the concentration difference, which is the driving force for my system. And the red parameters are the ones that you want to estimate. Basically, those are the unknowns you find, and it is they are what make it digital twin specific to your system. And this number balance is coupled with the mass balance, as you see, the dc/dt. Via growth. And similarly, without boring you, we have also heating cycles to engineer the size because having these heating cooling cycles actually help you grow your crystals a lot. And similarly, we have the same thing for dissolution and deagglomeration. Again, depending on your system, you can just write zeros, basically neglect these mechanisms if you don't have deagglomeration or agglomeration. Here again, for dissolution and deagglomeration, we have the equations. So this is the whole model for supersaturated and undersaturated phases because we have both of them. At least I had both of them in my projects. So this is the whole model, and you use basically MATLAB and solve these differential equations. But of course, okay, this is the one novelty is actually, this is a little difficult to solve. You have to look at literature and find some very powerful discretization methods. So what I use is finite volume method to solve these equations. So you have to transform the system of your equations in a certain way, but then it's just numerical. It's a numerical method. You just hit OD 4, 5 again, and then it solves it for you. And it spits out the crystal size distribution, basically crystal length, the concentration, and you can also calculate the crystal number. Those are all the data that we collect from our tools. So we can simulate by using these equations. And I talked about digital twin a lot, and I just want to show you how we call the model digital twin. So this was my workflow. If you just omit the benefiting part, these are the steps that you follow to make it digital twin. So I talked about data collection. I showed you my experimental setup. So I have the experimental data for crystal size distribution from offline tools, concentration of the drug from UV, and the crystal count from FBR and the beam. And I showed you that I have the required equations to simulate the system. So what I do, I basically use the same conditions that I have in my experiments and simulate those experiments. And now I can calculate the same data for crystal size distribution, concentration, and crystal count. And to create a digital twin, you want to minimize the difference with your actual data and what your model is simulating, so that you can say that, oh, my model is a good representation of what's happening in real life. And how we do that, we just write an optimization routine to minimize the difference between these experimental and simulated data. And in an iterative fashion, we change these parameters that I just showed you, which make up my model, until the difference is minimized. And then once I estimate these unknowns in this routine, I go back to the lab and do extra experiments, 1 or 2 or 3, and then I try to use that model with the estimated parameters to simulate the new experiments. And if they can be simulated well, if my model can predict the outcome, I call it a digital twin. I say like, okay, this model is a good representation of this system. And then this is by itself, just this optimization routine by itself is a whole other research. It took a lot of time for me actually, which from deciding on which routine to use to how to set it up and everything. And I generally use random search methods for optimization part. If you're interested, we can talk about it later. Okay, now hopefully I could set it up for you, like the experimental setup and everything and the mathematical modeling. Now I will show you some examples from my research where we actually follow these steps to do digital twin development and the process optimization. So I have to mention that my PhD was funded by Takeda Pharmaceuticals. It's a Japanese-American big pharmaceutical company. They came to us with some problems at hand. They wanted to grow their crystals in a certain way, and they asked us to do them for them actually, by using this smart manufacturing methodology. And in our first paper, we didn't use a real, I mean, the paracetamol, of course, is real, but it's a model compound. We didn't use their expensive cancer drug, but in later, we also used it. But just to show you the first paper, I'm going to talk about this model compound, paracetamol. So the first step is collecting data. To collect data, we did some special experiments in this paper. These are called direct design experiments. Namely direct nucleation control and supersaturation control. In these experiments, we use the tools that I showed you in a control loop as the detectors, and then we put a set point for both crystal count and supersaturation to do these experiments, and we collect data and plot them in a certain way to understand what's happening in the system. And these experiments are very important for us because they help us decouple the crystallization mechanisms to estimate the parameters more accurately, basically. So in the direct nucleation control, we use the beam FBRM tool to basically reach a set point for crystal count by implementing some temperature cycles, heating and cooling. So what's happening is I cool down the crystallizer, the crystallization happens, the crystal number increases a lot, and in the control loop, it tells me, oh, there are so many crystals, let's heat up the system to dissolve some of them. And it starts heating up the crystallizer, and some crystals dissolve and the number drops. It dropped too much, cool down again, and etc. So this is the cycling process. And if you collect the concentration data from this experiment by using UV, the other tool, and plot it against temperature, you have these loops, and these are very important for us because they help us to determine what are the nucleation boundaries are in our phase diagram. And this company told us that they wanted to grow crystals more than creating crystals. So what we want to do is actually we don't want to cross this secondary nucleation or primary nucleation lines. Basically, we want to stay here on the purple line, and you can do this by running a supersaturation control experiment. Now this time, instead of FBRM, you use UV as your detector, and basically you keep the supersaturation constant by cooling it down very slowly after putting some seed crystals into your crystallizer. And here, this is the real data from the experiment. And what I'm trying to show that we could grow the crystals without passing the secondary nucleation curve. And I'm going to show you the crystals as well. And the third experiment is just to give some initiative to industry. So this is the temperature profile. This parabolic cooling curve is the temperature profile obtained from this experiment. And then actually you can approximate this temperature profile by fitting 3 lines, because in industry, most of the time, they don't have these fancy tools, and they can just do this linear cooling. So that's what we do for them and say, hey, okay, if you do this experiment, you will grow your crystals without nucleating, basically the reproduction of this experiment. And that was nice, but in our system, we had this problem of agglomeration, and they didn't want agglomerates too. So only implementing this experiment was not enough. Yes, the crystals grew well, but they started agglomerating, creating surface defects, and we didn't want that. So we said that, okay, now we need the model, and we need the digital twin so we can do process optimization to avoid these agglomerates as well. So we collected the data from these experiments because that was really good data, decoupling growth from nucleation and everything. And we wrote our model, very similar to what I just showed you, to estimate these red parameters. And by running that optimization routine, we estimated our parameters shown in red. And then we went back to the lab to do another experiment to validate this model. And here you see the concentration data, crystal size distribution, and also the crystal number during the experiment. And the model did a good job in predicting, did a very good job in predicting the crystal size distribution, the product distribution, and in mimicking the crystal count. We can also talk about the discrepancies. This was a very long paper, so I'm just summarizing it up. If you have questions, please ask. And it did a good job in following the solubility curve, especially for heating up and cooling down for the second time. And we said that, okay, this is a good enough model. It can predict what's going to happen very well. Let's use this model to do process optimization. And then our objectives were as I mentioned, to minimize agglomeration, to minimize small crystals. We call them as fine. Fine index is just a way of calculating the small crystals. And then we also wanted to make sure we have smooth operation. And after we did the process optimization, basically the math told us to do this experiment to implement this temperature profile shown in black. And then we repeated this experiment 3 times just to show the reproducibility and it works well. And then we could produce the single big crystals as we wanted. So the difference is, you may not see it very well, but all these crystals are agglomerated. They're stuck to each other. And this is, although they are big crystals from the previous experiment and show, they have these surface defects and they are agglomerated. That's something we didn't want. So by implementing this temperature profile, we could see that, oh, okay, we have these more smooth surface, more single, like large crystals and etc. So that was one proof of concept study that we did with a model compound paracetamol. And actually, Takeda people liked it very much because they didn't have the understanding of temperature cycles. Because one more important thing about temperature cycles, they help you a lot to grow your crystals. And they implemented it in their real system to produce a cancer drug. And then they get approval from FDA in the US, because you need that approval basically to produce a drug, to make it, commercial. So yeah, that was very nice to see, like, oh, I did something and it was actually useful. And then they decided on working with us more and more. And then I'm going to show you another project within the same workflow. But this time I used their real cancer drug to do the same thing, basically. This was a little challenging because what I showed you before was a model compound. It was very nice. It was more like spherical almost. It had that nice shape. And all these tools they're calibrated by using spherical crystals or spherical particles. And when you use these needle-like crystals, these long material, you have discrepancies, and that's the challenge in actually this data-driven frameworks for pharma, because most of the time the drugs have this needle-like crystals. But that was good because this is research, you need challenges. So for this experiment, for this work, I didn't do the previous experiments I didn't do the control experiments. So I basically designed some experiments some experiments with different cycling, with different temperature profiles, because now we know we need cycles to grow these crystals up to a certain point. And then in this work, we also wanted to make use of the tools that we are using more. So we formulated the crystal count data in a way that it can help us do parameter estimation more accurately and faster, because now we have this new term in the parameter estimation routine. I'm not going to go into detail, but that was one novelty of this work, so that we also wanted to show industry that this commonly used tool can be used in basically model development as well. It's not only for data collection, or it's not only for monitoring the system, but you can actually use it for model development. That was one novelty. And the other one was these crystals displayed demonstrated a size-dependent growth. So small crystals didn't grow fast enough, but large crystals were growing fast. So there was this like broadening effect due to that in the crystal size distribution. So we went back to the literature and looked at the basically the models that are already there for size-dependent growth. And then we also came up with our own formulation for size-dependent growth to, describe the system the best. So you see the functional behaviors of these size-dependent growth equations. So the one we came up with two, actually, equation 15 and 14. Here I show equation 14 and 15. I boxed equation 15. It's the most complicated one, and it is the one worked the best, actually. But what we did, we decided on using four different equations for this model, and then do the parameter estimation with four different models. And we estimated all the parameters with, again, these four different equations for size-dependent growth. And then to call it digital twin, we went back to the lab, did more experiments, and after that, we decided on which model to use as digital twin by looking at the goodness of the fit for product crystal size distribution. So from these two experiments, the real experimental crystal size distribution is the blue one, the bright blue one, and the others are this is the seed crystals, basically the starter crystals. You don't have to care about it for now. And you can look at the other black dashed very dark blue, and the other dashed blue lines. So equation 15, this one, showed the best fit. And that's why we chose the model with equation 15, the one we developed. And then we said that, okay, this mimics the system the best. We're going to use it as a digital twin to do further process optimization. And we created 3 scenarios to make a point. We knew that we needed temperature cycle. So we did 3 different process optimization for 3 scenarios, one with 1 cycle, one with 2 cycles, and 3 cycles. And our aim was to maximize the crystal size, basically median size we call D50, minimize the broadness of the crystal size distribution, because we want uniform product. If it's narrow, it means that your crystals, almost all of your crystals have very similar shapes and sizes, not shapes, sizes. And basically to minimize the aggressiveness of the heating and cooling. And after optimization, we had this trend. It was very nice to see. So the optimization told us, if you have 1 cycle, you better do it in a very deep fashion, like you cool it down and then you heat it up for a long time again. But if you have multiple cycles, you better do it at a high temperature range if you want large crystals. And then I took 2 of these scenarios, 1 cycle and 3 cycles, and I did the experiments, and you can see how the crystals changed actually with increasing temperature cycling at the higher temperature. And that was very nice to see. Because it shows that what you did actually worked. It's true. You could grow crystals larger. Here you can also see the simulated crystal size distributions. And if you have 3 cycles, you can see the crystal size distribution shifted towards right, which means that you will have larger crystals, and it was narrower than the other one. So less variety in your product. And then, yeah, again, that was very nice to see, because we did this fairly short time, but of course there's a learning curve for me as a PhD student. But at the same time, Takeda people were like trying to do this by themselves without any model or optimization guidance. So they did a lot of experiments for more than 2 months, because each experiment takes almost 2 days for them. And then they also concluded at the same point, oh yeah, you were right. Yeah, we need to cycle it at that higher temperature to have larger crystals, and we better have multiple cycles. So again, that was one nice thing to see what I did actually worked well. And that was another, we just submitted this paper. So that was another story. And the last thing I'm going to show you is more about hot topics. This time, we only had one tool. I did this project during my this summer, actually, during my internship at Genentech. It's a Roche Group company. It's a biotech company in California. And they had a problem. Again, they had this like cool tool, which is a camera, again, to monitor their systems. And this camera is a little different than what I use. It automatically gives you the crystal size data. So which this D50 is the median crystal size. You can think of it as a median crystal size, and the crystal count, and the temperature, and some other information. And the problem was that the data they collected said that, oh, your crystals are at around like 60 micrometer, but actually their crystals were much larger than that. So what they collected were around 130 to 150 micrometers. So there's a huge discrepancy. And they wanted someone to basically use this image data and give them more accurate size information. And originally my project was about that, and then using that size information to build a model, again, like I showed you, to do some process optimization. But the time and the data, actually not the time, but the data we have was not enough to do that fully, because they didn't have the solubility information and everything. And most of the time, industry doesn't have all the information that I have in my research. So I said that, okay, I want to deliver something to you. So let's focus on developing a tool which will help you at least, do image analysis and then measure your crystals more accurately. So during this time, I had to learn how to do image analysis and use convolutional neural networks, and also to develop a user-friendly app for them. So when I'm gone, they can continue using that for their experiments. So long story short, there's a lot of things to talk, but I'm just going to skip. You see how I learned how to do image analysis on MATLAB. You see how we can transfer these images into like colorful ones. Even to the human eye, there is no crystals in these pictures, but actually there are. So I had to learn how to do this in a very uniform way for all the images they have. So by the way, for each experiment, they have thousands of images. So you have to, have a methodology for doing that. And then I wrote a code, to do some noise elimination, because after you do the image processing, you still have a lot of noise, and noise is not your friend when you want to do image analysis and neural network training. And then also I didn't have any idea about neural networks. So I had to learn, at least I had to have some idea which neural network to use and how to use it and everything. There's a thing called transfer training. So it is useful. We can talk about it if you're interested. I had to learn all these things. And then at the end, I created the small app for them. And all they needed is their images, basically. They can just do the color filter, application to change their images so that they can detect these crystals better. And they can eliminate noise actually by selecting the crystal area and the noise area. And then they can calculate the median size for their crystals throughout the experiment by using those processed images. So this is the median size and how it changes throughout the experiment, and the crystal count per image, and the crystal size distribution and how it changes from black to light blue. And then they could also do neural network training. At this point, it is a little redundant, but they wanted to include it because that was the hot topic. Everyone talks about neural networks. So I was like, okay, let's do it. And I gave them 4 options for neural network training. And actually, if you have a bunch of experiments and thousands of images from those experiments, neural network training could be useful. Basically, you can use one of your experiments to train a neural network, and then you can use the trained neural network to analyze your other experiments in terms of calculating the crystal size, like D50 and everything. So that was nice to have. At least it was like a nice learning experience for me. And this tool does everything for you, basically, automatically. You don't need to know or much about neural networks, or you don't need to do the folding and other things. It's just automatic. You can compare, and I think the most important part is the data analysis. I think that's the real part, because what they wanted to know actually how the process parameters, like the stirring rate, how they stir the reactor or crystallizer, affects the crystal size. So I created the small menu for them so that they can do like fast correlation analysis to see if the cooling rate was affecting the crystal size a lot or not. And you have these not a number values because I didn't put anything for anti-solvent addition rate, and etc. So for the validation, I used one of their extra experiments, and the tool I developed told me that in this experiment, the crystals were between 20 to 60 micrometer. And this is the SEM electron microscopy image for those crystals. And if you look at the scale, this is 5 micrometer. It was actually very accurate. The crystals were between 10 micrometers to 70 micrometers. So that was nice to see. I also created the crystal size distribution. And this is another tool which calculates the crystal size distribution for you. And if you look at the median size around 10 micrometer, it was very accurate in that sense. So that was also another thing, why it is important, how it is related. This is, again, a data-driven tool. Like industry, academia, they have been using these tools to collect data and like do some experiments. But now we can actually use this data to develop these like tools and help them to have some idea about the process and design their future experiments or materials and everything. So that was the point. And now they actually use it. They say that, oh, this is working well. They've been using it to understand what's happening in their system. So that was nice. Okay, so overall, I think I better summarize, wrap up now. Just about my PhD research life. So this is my last year. I just finished my 4th year, and hopefully I will graduate in December. So I've been working with Takeda Pharmaceuticals, and that's something that people do a lot in the US. They collaborate with industry a lot, so that industry benefits from cheap workforce students, and it's also good research. Good research for the students. So I've been working with Takeda, and I've learned a lot how I can use my research for industry and for real applications. We submitted and published other papers on 2D modeling for shape control of the same drug. I'm sorry. And then I also had other projects, like we had a very good collaboration for 2 years with Professor Lynn Taylor from Pharma department. I'm sorry. On another cancer drug. This time it's just a dissolution and breakage of a drug in another system, hot melt extrusion. That's also something industry uses a lot to produce the tablets. Basically, they just melt the crystals in a polymeric media, and they just create the tablets like that. I also did the continuous CBD crystallization for Mike Tyson. That was very fun. I haven't met him, but I have met his friends actually. This was very interesting to see in the US. So we set that system up and did everything, like we're talking about engineering, doing continuous crystallization and everything. And these people came and they said, like, oh, don't talk to me with like fancy terms. Don't talk to me in engineering terms. Just tell me, can you purify it or not? And this person from the company, he literally came and sniffed the CBD to understand if it was pure enough. And that was very interesting to see. I wasn't expecting to see in a research institution in the US, but it was fun. And that was one fun project. So we are also writing the paper from continuous CBD crystallization. And then I've also learned a lot, how to deliver things, how to make useful things for people. I just showed you, these are this is one application I've developed for Takeda so that they can simulate their experiments instead of going there, doing it in 2 days. And during this time, hopefully by the time I graduate, hopefully I will have a bunch of papers. These are the journals that we generally publish. It's not science or nature because it's mostly engineering, but I have friends who publish in science and nature too. So if you are interested in such things, go for it. You can still do it. And with that, yeah, I would like to thank many people. They say that all it takes is one good teacher, and I was very lucky to have many of them. And I would like to thank to my advisors throughout my graduate years, and everyone, and also Professor Zoltan for giving me this opportunity. I learned a lot from him as well. And with that, thank you for your attention.